All right, so today we're going to be talking about adding and subtracting rationals. So already at this point, we've talked about multiplying, dividing. Adding and subtracting is a little bit different, but there are some common elements that you're going to see between these. There's also going to be a lot of common elements between this as well as adding and subtracting fractions, which you would have learned, of course, in previous math classes. Anyway, let's get going. So today's plan is, like I said, we're going to move away from multiplying and dividing, introduce how to add and subtract them. So remember when we multiplied or divided rational expressions, we had to factor, in other words, simplify them first. Adding and subtracting rationals is arguably a bit more challenging than multiplying and dividing. You'll see why in just a second. It has a lot to do with why fractions work that same way. But ultimately, there is a lot in common. So anyway, let's get going. So first of all, before we do any adding and subtracting of rational expressions, I want to remind you how we add and subtract fractions. So think back to when we were adding or subtracting fractions in previous math classes. Like for instance, if I gave you 2 out of 5 plus 5 out of 7, how do we go about doing this? Well, what you might remember is in order to add two fractions together, they have to have a common denominator. There's a couple different ways we can do this. Some people try to find what's called a lowest common denominator, where you start thinking about everything you can multiply 5 by that might give you something that also you can multiply 7 by something to get the same number. Honestly, in reality, I think the easiest way to add or subtract fractions to get that common denominator, let's just multiply by the other fraction's denominator. When you do this, you need to multiply both the top and the bottom of each of the fractions by those numbers. The reason being is if we take 2 out of 5 and I multiply it by 7 over 7, that's going to change the denominator. It'll also change the numerator, but because it's 7 over 7, it's like we're multiplying by 1. And when you multiply by 1, nothing ever changes. It's still the same value. Same with 5 out of 7. We could multiply that by 5 out of 5. So again, I'm multiplying this fraction by the other one's denominator. What this is going to give us, I'll just do it down here. This would be 14 out of 35 plus 5 times 5 is 25 out of 35. Now they have a same denominator. And hopefully what you remember from previous math classes is if you're adding two fractions together, as long as they have the same denominator, you just have to add the numerators together. So it's going to be 14 plus 25, which is 39 out of 35. The last step always when we used to do this is we'd simplify it. In other words, we'd look to see what we could divide both the top and the bottom by. Spoiler alert on this one, there's nothing we can divide both the top and the bottom by. So this is actually considered simplified. Now you're going to find today that this process for adding and subtracting fractions actually translates really well to adding and subtracting rational expressions, which remember, rational expressions have polynomials on the top and the bottom. Let's see how in just a second. So here's the process between adding and subtracting rational expressions. It'll make a lot more sense when we see some examples, but it's still important to know there's some fill in the blanks that you got to fill in here. With rational expressions, the process is similar. You still need to have a common denominator. That's a little bit weird with rational expressions, though, because, of course, our denominator is going to be some sort of polynomial, right? And oftentimes we want it totally factored, which also complicates things. Well, here's the steps that we want. Step number one, when you're adding and subtracting rational expressions, factor and simplify each rational expression if possible. So just factor and simplify them separately. We're not combining them together like we did with multiplying and dividing. Just factor and simplify them separately. Then step two, make the denominators identical. What that's going to involve is it's going to be multiplying each of the fractions, both on the top and the bottom, by the other fraction's denominator. Now, because it's in factored form, we can often take some shortcuts here. You're going to see that if any two fractions have the same piece in the denominator, like maybe they both have like an x plus 2 down there, you don't need to multiply each fraction by x plus 2 because it's already there. Basically, just multiply by the pieces, these binomial pieces, that are missing from the other ones. That'll make a lot more sense with an example, but these are the steps. Anyway, step three, add and subtract only the numerators. Here's a big thing though, and this is super annoying. This is what makes adding and subtracting much more difficult. You might want to expand them back out first. So in other words, everything we've done with multiplying and dividing, we've often just left it in terms of like a factored form. I never said, oh, double dip it back through, like expand it out using distributive property. We just never needed to. But with adding and subtracting these, you do. You really do, unless very rare cases that you don't. But generally speaking, you do. Anyway, last step, factor and simplify once more if possible. That's kind of a funny one. Sometimes once you simplify everything doing this, you can do it actually one more time and clean up anything else. So that doesn't always happen, but It's a good thing to keep an eye out for. And then as always, you need to list your NPVs as well. That's your non-permissible values. As you can see right now, that's a lot, right? There's no point in memorizing these steps. It's more just a matter of thinking, how does this compare to adding and subtracting fractions? You need to have a common denominator. And because this is rational expressions, we need to make sure everything's factored as well. Anyway, enough of me rambling. Let's have a look at an example. First example are like pretty small rational expressions. There's no huge polynomials in this. We're just keeping it relatively light. We have 5 over 3x minus 7 over 2x squared. The number one thing that we have to do is factor this. But here's the thing. If you look at each of the 4 pieces here, it already is factored. Factor just means written in a form where everything's multiplying together. It all is, right? So that brings us to the next step. The next step is we want to make the denominators identical. In a case like this, because we have numbers as well as variables, we have to kind of think outside the box and think, what would we need to multiply both sides by in order to get the denominators to be the same? Well, because this is 3x and this is 2x squared, I feel like I can multiply the top and the bottom of this left fraction by 2x, not 2x squared, just 2x. And the reason for that is it's going to make the bottom 6x squared. Again, this bottom is going to be 6x squared. Maybe we'll even write it down here. 2x times 5 is 10x. That's a gross looking 10. Let me fix that. 10x over 2x times 3x is 6x squared. For this other fraction, we could multiply the top and the bottom to turn the bottom into 6x squared. We could multiply it by 3 over 3. That's going to produce 21 over 6x squared. And notice now they both have the same denominator. They both have a 6x squared down there. Now here's the thing. If you had multiplied straight up just by the other one's denominator, like hit this one with 2x squared over 2x squared and this one with 3x over 3x, that would also force it to have the same denominator, but you would have an excess amount of x's up in the top, and that might not be the best. Anyway, so now that we have these two having the same denominator, let's just subtract the numerators. There's nothing to expand out here. We just subtract the numerators, so it's 10x minus 21. Not much I can do with that, so it's just 10x minus 21 all over 6x squared. This brings us to the final step. If there is anything you can do to factor this, excuse me, please do. In other words, 10x minus 21, you should ask yourself, is there anything that comes out of both those numbers? Well, the reality is in this case, there isn't actually. So the good news, we're actually all done. So that would be our final answer if we subtracted those two. But again, don't forget, you need to list your NPVs. NPVs are just the values of x, or whatever your variable happens to be, that makes your denominator equal to 0. Throughout this whole thing, it just looks like it's going to be x cannot equal 0. Because if x was 0, this would be 0. If x was 0, this would be 0. Both ways, we'd have x cannot equal 0 as an NPV. Anyway, let's try another question. So this one looks a little chunkier, but the good news is the denominators are just plain old regular numbers. There's nothing super crazy going on here. So we have a denominator of 4 and a denominator of 6. There's a couple different ways of doing this. If you're really keen, you can think of like a lowest common denominator between these two. I happen to know that if I multiply 4 by 3, I get 12. And if I multiply 6 by 2, I get 12. That works really great. If you're not comfortable with that, you can just multiply each of these fractions by the other one's denominator. Whatever floats your boat. I'm going to stick with the lowest common denominator, though. I'm going to multiply by 3 over 3 here, because that'll turn the bottom into 12. And on this one, I'll multiply by 2 over 2. So if I multiply by 3 over 3 here, the 3 actually has to double dip its way through. This is going to become 3 times 2x is 6x. 3 times minus 3 is minus 9. Over 3 times 4 is 12. Plus, on this one, 2 is going to have to double dip through here. 2 times x is 2x. Plus 2 times 7 is 14. And again, this is going to be over 6 times 2, which is 12. Now, here's what's kind of interesting. There's kind of a lot going on here. 6x minus 9 plus 2x plus 14. That's all what's going to go on the top. We can gather some like terms here. A little word of caution. When you see a subtraction question, like I know this is an addition, but if we see a subtraction question, the subtraction sign would have to hit everything on the second fraction. So just be careful with that. We'll see that in a little bit, but just something to be wary of. Anyway, 6x plus 2x, well, that would be 8x. And then minus 9 plus 14, I'm pretty sure that's going to be plus 5. And then that's still all over 12. The last thing to do here, of course, is to say, is there anything that we can do to factor this any further? If you look in the top, there's nothing that comes out of both those numbers. So I'll say this is done. One thing we always have to do as well is list our NPVs. Remember, NPVs are variables that make your denominator equal to 0. Well, notice our denominator here was just 4 and 6, and then they both became 12. Notice how there's no x's or any other variable down there. This actually means there's no NPVs. So if we want to make ourselves just like really clear here, we can just say no NPVs. But on a question like this, honestly, just because there are no NPVs, you don't even have to list that at all. So, all right, moving on. Next question. 3x over 5 minus 2x minus 7. This one's kind of similar to the last one. We just have numbers in the denominator. So in order to get those numbers going, let's just find a lowest common denominator. I think we straight up just have to multiply by the other one's denominator here. So it's going to be 4 over 4 on this one and 5 over 5 on this one. What that's going to do is on this one, 4 times 3x is 12x over 4 times 5 is 20 minus 5 has to double dip through this because there's two pieces. That's going to be 10x minus 35 over, that was a terrible sign there. Hold on, let's fix that. Over 20. Now, this is what I was alluding to on the last slide. Notice we're subtracting this whole chunk. Imagine this whole chunk as being in brackets. This minus sign has to trip its way through those brackets there. So when we simplify this as a single fraction, it's going to be 12x minus 10x, and then minus 35, which is plus 35, and that's all over 20. We can clean up the top a little bit because those things are going to combine. 12x minus 10x is, of course, 2x. We still have the plus 35, and it's all over 20. And I know we've had no luck with this so far, but as always, our last step is to say, does anything come out of those, right? Is there anything we can factor? Well, between 2 and 35, there's nothing that factors out. So once again, bit of a buzzkill. There's nothing we can do there. So that's just going to be our final answer. Also ask yourself, NPVs. Do you think there's going to be any NPVs in this question? Well, if you look at the denominator, there's never any x's down in the denominator. Just 5 and 4, and then it became 20. Because of that, once again, there are no NPVs. Kind of unusual, but it happens. All right, next slide. All right, this is where things are starting to get a little spicier here. So holy smokes. Remember, number one goal, make sure everything is factored. In this case, it looks like it is. Number two goal is to get the denominators to be the same, right? So if we look at the denominators there, 2x and x squared, think about what you have to multiply each one of those by to turn it into the other. This guy just only has one x. So I feel like I'm going to need to multiply this one by x over x. That would turn the bottom here into 2x squared. This guy then, to turn it into 2x squared, it's just going to need a 2 over 2. Let's expand this out. So remember, on the top, this is going to have to double dip through. So this is going to become x squared plus 7x over 2x squared minus, those minus signs are always so tricky, so minus, double dip the 2 through this. It'll be 2x minus 4 over 2x squared. And then again, the reason those minus signs are tricky is because we're subtracting this whole thing, which means this minus sign has to trip its way through the brackets there. So this is going to become x squared plus 7x, because the first thing stays the same, minus 2x, and then minus 4, which is plus 4. And this is all over 2x squared. One last step here. Let's just make sure that we clean up this. We have 7x minus 2x. Well, that's going to be 5x. So we'll have x squared plus 5x plus 4 all over 2x squared. Now, looking at this, we could factor the numerator if we really wanted to. That's just a normal sum product rule question. But I can tell you right now by looking at that, if we did factor it, it's just going to give us two binomials. And that's not going to cancel out the 2x squared. So if you're not believing me on that, you can always factor this further, but we don't actually need to. It's totally valid just to leave it in this expanded form because there's nothing that's going to cancel out the 2x squareds. We're not going to be able to pull a 2 out of all this, and we're not going to be able to get an x, or definitely not an x squared all by itself when we factor this. So I'd consider this done, but we do need to list our NPVs. Our NPVs in this case are just going to be x cannot equal 0 and x cannot equal 0, so just one. X can't equal 0. Whew. So this is quite a bit, right? But as we've seen, we've been slowly increasing the complexity of this. Each and every question that we've dealt with has had like a little extra bit of a twist here. But what I've hoped you've noticed so far is we haven't seen any questions where we've had to like straight up factor anything right away. Like we haven't had to use the sum product rule or difference of squares or anything else. We've just been able to, multiply things through and then subtract and go to town, right? It's been all good. That's not usual though. There's going to be a lot more difficult questions where we do have to factor. So let's see. Not quite this one. Darn, I was thinking it was the next one, but not quite this one. This one's getting close. So this one's interesting because we're throwing y into the mix, right? So let's look at the denominator here and ask ourselves, what would we have to multiply by in order to like make those denominators the same? This one only has 1x, but this one has x squared. So I can tell you right now, I'm going to need an x over an x to bump this up to an x squared. This guy, of course, has a y that this one does not. So I can tell you also right now that this is going to need a y over a y to get it on the same level as this other one. Let's see where this gets us. If we go x times 2x, this gives me 2x squared over x times xy is x squared y, plus on this one, 4 times y is 4y, over x squared times y, well, that's just x squared y. Notice now they have the same denominator. We can just add the numerators together. This one's actually kind of lame. It's just going to be 2x squared plus 4y over x squared y. And you can ask yourself, is there anything else we can take out of this? Well, I will actually kind of humor you on this one. On the top, we can take a 2 out of both of those things. That's going to be 2 times x squared plus 2y. If I divide both those things by 2, and this is still over x squared y. But the reason I say I'm humoring you on this one is that 2 that I pulled out, that does nothing. There's nothing more that came from this. It's kind of like that last question where I said, well, I could use sum product rule. It's not going to get me anywhere, though. That kind of happened here, too. So this is a fully factored answer. Nothing cancels out. That's as good as that's going to get. We do need to list our NPVs, though. Our NPVs, we have 2 different variables in the denominator. It looks like it's going to be x can't equal 0. And y can't equal 0, because if either of those pieces were equal to 0 anywhere along here, you would have had a divide by 0 issue, right? All right, so I feel like we're beating this to death. So here we go. Now this is where meat officially hits the menu. We've got polynomial denominators. So this is where things are a little scarier, but don't panic. It's the same concept as what we've just been doing. We just need to make sure our denominators match. So as always with rational expressions, just factor everything first if applicable. Hasn't really been very applicable with the examples we've seen so far, but believe me, it is coming. Remember, with adding and subtracting, that you must have equal denominators. They must be the same. If everything is factored, this becomes much easier. Let me show you what I mean with this example here. We have 3 over x plus 2 plus 7 over x minus 7. If we imagine these as factors, because they really are, they're all on their own. If we imagine these as factors, I always like thinking about adding and subtracting rational expressions as like just building blocks together until you have everything that matches. What I mean by that is this fraction on the left has an x plus 2 block. This one on the right has an x minus 7 block. They're not matching blocks, but you can just give the other fraction the block that the other fraction has on the denominator. So on this one here, the 3 over x plus 2, why don't I just give it an x minus 7 on the top and an x minus 7 on the bottom. And for this one, we'll give it an x plus 2 on the top and an x plus 2 on the bottom. So I'm just multiplying the top and bottom of these fractions by the other one's denominator. Let's see what this gets us. We really should expand these out as we go, or at least just the numerator. The denominator, please, by all means, the denominator, leave it factored. It's way better. For the numerator, 3 is going to double dip through here. That's going to give me 3x minus 21. Over, we technically have x plus 2 times x minus 7, plus, for this one, 7 is going to double dip through this, so it's going to become 7x plus 14, because that's 7x times, or 7 times x and 7 times 2, over x minus 7, x plus 2. Now, the order that the denominators are multiplied in, it doesn't really matter, because when you multiply numbers, order doesn't matter at all. Those denominators are now matching. That means I can add my numerators together all at once. Because this is just an addition question, I'm not going to worry about writing a middle step. If it was a subtraction question, remember the minus sign would have to, dip through the second fraction there. But because it's addition, you just add as you see, right? So 3x plus 7x, well, that would be 10x. Negative 21 plus positive 14, well, that would be minus 7. And this is over x minus 7 and x plus 2, or vice versa. Those could be written in another order. Final step here is make sure everything's factored on the numerator. That looks like we can't factor anything because no number comes out of both 10 and 7. So I would actually say, you know what, this question's done. We'll box that as our answer. We do have to list our NPVs though, as always. So our NPVs in this case are going to be x cannot equal negative 2. And for this other one, it'd be x cannot equal positive 7. Because again, those are the values that would make your denominators equal to 0, as we've seen in previous lessons as well. All right, so that one was just a starting point. Let's see what else we can throw at us. Okay, yeah, here we go. This is more in line with what I want to see. So this next one, 2 over x squared minus 4 minus 7 over x squared plus 5x plus 6. I know it says we'll do this one together. This is just a video lesson though, so follow along as we go. This is about our only shot that we got at this. Unless you want to pull like a SpongeBob SquarePants or Dora the Explorer thing and shout at the screen. What do you think we got to do first? We have to factor everything. Hopefully some of you guys mumbled or shouted or even spoke over me as I was saying it. We got to factor everything. So to factor everything, start with this thing. Like, I mean, 2 and 7, there's nothing we can do up there. Nothing going on. But x squared minus 4, the factoring method we'd have to use on that is a difference of squares. Both of those are square rootable. So like we've seen before, this is going to be 2 over, that would be x minus 2 and x plus 2. For this one, minus 7 over this thing here, x squared plus 5x plus 6, that's just a normal old sum product rule. So we're looking for two numbers that have a sum of 5 and a product of 6. I know this is kind of a puzzle for some of us. It's like, oh, gee, what two numbers would add to be 5 but multiply to be 6? I've always told you, focus on the product first. Think about what numbers multiply to give you 6. I think the best two numbers here are going to be 3 and 2, because 3 plus 2 is 5, 3 times 2 is 6. What do we do with 3 and 2? Well, because this is just a normal sum product rule question, we just write them as the factors. X plus 3, that's where the 3 is, and x plus 2, that's where the 2 is. So we have this factored. We haven't changed anything yet. We've just changed what it looks like. Nothing's really moving. But here's what we really need to focus on. Look at the denominators and what pieces they have in there. This guy has an x minus 2 and an x plus 2. This one has an x plus 3 and an x plus 2. Notice they both have an x plus 2. That's pretty convenient. The only difference here is this one has an x minus 2 that this one doesn't have. And this one has an x plus 3 that this one doesn't have. So how about we give it the missing pieces? Just to really drive this home, how about I change color to blue real quick? This one on the left needs an x plus 3 on both the top and the bottom. This one on the right needs its missing piece, which was x minus 2. That was the one that the other guy had that this one did not. So x minus 2 on the top and the bottom. Don't worry about the order on the bottom too much, because again, with multiplication, order doesn't matter. You can just write them out in whatever order you want. You multiply numbers together, it's all the same. What is important, however, though, as annoying as this is, we need to double dip this stuff through our numerator. I'm also going to caution you here because this is a subtraction question. So what I'll recommend is double dip this through, but let's not combine it as a single fraction just quite yet. So on this first one, we're going to have 2x plus 6, because that's what happens if I double dip through, over x minus 2, x plus 2, x plus 3, minus this, if it double dips through, is going to be 7x minus 14 over x plus 3, x plus 2, x minus 2. The reason I did this middle step here is just because when we do subtraction of two rational expressions, it can be a little bit scary because, again, this minus sign needs to hit both of those things here. So if we're really careful, as I'm combining this now into one fraction, 2x minus 7x, well, that would give me negative 5x. Be really careful with this next one. 6 minus negative 14, that's a double negative, so that's like saying 6 plus 14. That's going to be positive 20. And again, this is all over x plus 3, x plus 2, and x minus 2, in whatever order you wanted to write those. There's one last thing I want to do here. I don't believe it's going to cancel out, but let's just check just to be sure. On the numerator, I can factor out a -5. This is going to be -5 times, if I divide both of these by -5, I get x. 20 divided by -5 is -4. And this is still all over x plus 3, x plus 2, and x minus 2. Nothing cancels there. It would have been pretty awesome if this x minus 4 that we just discovered canceled out with one of these things on the bottom. That would have been great, actually, but it didn't work that way, and that's normal. So let's just box this. That's as far as that goes. Of course, as always, we have to list our NPVs. Look at the factored form all the way through. Nothing cancels, so there's no surprises. It'll be x cannot equal, for this one, -3. Fix that 3 there. There we go. This next one here would be x can't equal -2. And this last one over here would be x cannot equal +2. Ooh, it's quite a lot. So it's been a long lesson so far, but I think we've only got one more. Let me actually just double check. This one. Oh, no, two more. Okay, here we go. So 2 more questions. I was wrong. Try this one. It'll simplify fairly nicely. I'll tell you what, actually, I want you guys to pause the video here and give this one a try. You can work with a partner if you wish, but give this one an honest try. Factor everything first. Okay, pause the video here. I'll do this in a second. All right, so now I'm going to go over this. Hopefully you had a chance and had a little bit of success at this one. It will simplify fairly nicely. This top part up here, if we're going to factor that, I can pull an x out of both those things. That is not a difference of squares up there, even though it kind of looks like it. It's going to be x times x minus 1. Just remember, if we're pulling an x out of this, there's still something there. It's a -1 that's going to hold it, because think about if that x double dipped back through. Something would have to be there, right? Over x squared minus 25, that's a difference of squares. Both of those are square rootable, so that's going to be x minus 5 times x plus 5. And we're subtracting x minus 3 over x minus 5. I just threw brackets in there because why not? It doesn't really hurt anything. Notice this one has an x minus 5 and an x plus 5, but the one on the right has only an x minus 5. We're going to need to give that an x plus 5. I'm just going to change colors again. We'll give it an x plus 5 on the top and the bottom. Now this is annoying, but of course when we subtract this, we should always expand our numerators out. This numerator in particular is going to be pretty painful, but let's see how it works. The one on the left's not too bad, just double dip x through. I know this seems redundant because we had pulled it out in the first place, but I was hoping we'd see an x minus 1. We didn't, so it's not the end of the world. That's just x squared minus x over x minus 5, x plus 5. Minus, this thing's going to be a bit of a pain because it's a binomial times a binomial. X times x is x squared. X times 5 is plus 5x. Minus 3 times x is minus 3x. Minus 3 times 5 is minus 15. This is all over x minus 5 and x plus 5. Now we can combine it as a single fraction, right? Be careful, we're subtracting here. That means that subtraction has to hit all of these pieces as it comes through. So be careful. Do it one piece at a time. X squared minus x squared. Well, that's nothing. Those are gone. I'll just knock those out. Great. Minus x minus 5. So negative x minus 5 is negative 6x. But wait a minute, then we have another minus 3. Oh, but we have to hit a minus minus, so it's actually a plus 3. Maybe we'll bear with this a little slower here. So I'll show you negative x minus 5 is negative 6x. So those are gone. But then we have to minus 3. So that's like saying plus 3x. That gives us negative 3x because negative 6 plus 3 is negative 3. This last piece is kind of on its own, minus negative 15. Well, that's just going to be plus 15. And then this is still over x minus 5, x plus 5, because we do not subtract our denominators. Now you might think, oh, okay, well, that's simplified okay, but there's actually one more thing we can do here. Notice I could factor out a negative 3 from both of these things. If I factor out a negative 3 from that, that gives me negative 3 times x. 15 divided by negative 3 is minus 5. Over x minus 5, x plus 5. And what do you know? Finally, we see a question that actually has something cool that happens with it. Notice what's on the top and the bottom. There's an x minus 5 there. Those are both going to cancel right out. And this is going to leave us with negative 3 over x plus 5. And there's nothing more we can do there, so we'll box that answer. One final thing I have to do on this, though. List your NPVs. I'll just list them up here because I have room. Look at your fully factored form. Looks like there's just 2 NPVs here. It's going to be x cannot equal 5, and x cannot equal -5. And that's about as good as we get it. So, all right, so this last one, tell you what, this one is actually a really long and tough one. I wouldn't actually suggest doing this in a YouTube video. It doesn't really translate well. So tell you what, for now, you can just kind of either, you know what, just ignore this one for now. We can actually cover this another time when I'm back in class, or if you prefer, if you feel a little bit brave and bold, you can give this one a try on your own, but I'm not going to mandate it. So we'll just call it there. Anyway, what this leads us to is, for practice, you can work on page 336, questions 1, 2, 5, and then those other ones that are listed there, of course. But let's be honest, most of you will probably want to work on your chapter 6 assignment. At this point, you can now complete up to question 3B. So there's only a couple extra questions from the last lesson that we can now add on to. One way or another, though, if you have any questions, please reach out and I can help you when I get back. Best of luck.